All right. Let's start with questions from this assignment. Angeli? 47. Oh, you know what? Let's do. I will happily do that for you, Ange. Let's do this first, though. Let me read through the even solutions. That'll probably help people in terms of gauging what they have a question for. I don't want to read the odds because you guys have the odds already. You should be checking those. If you haven't been, shame on you. 42 is negative 435 over 106, comma 783 over 106. 44 is 261 over 73, comma negative 696 over 73. 46 is 61.56 pounds. 48 is 95.22 pounds. And 50 is 99.06 pounds. Okay. Do I need to repeat any of those? 50, 99.06. Okay. All right. Anjali, we wanted to do 47 still, right? Okay. So this reads, a crate of negligible weight is being pulled up a ramp at an angle of elevation of 38 degrees with a force of 120 pounds. The ramp has an angle of elevation of 25 degrees. What is the amount of force being directed up the ramp? Okay. So when I read this, I hear two vectors. The fact that the crate is of negligible weight, what that tells me is that the gravity vector is 0. We don't have to worry about the gravity vector. But I have a pull vector and a ramp vector still to worry about. So I'll define the pull vector by doing the magnitude of that vector, 120, times cosine of 38, and then 120 sine 38. My ramp vector, I'm going to choose to have magnitude 1. And since we're moving up, it'll be positive 25 degrees. And then, so I have 1 sine 25, 1 cosine 25, 1 sine 25. Okay with that so far, Ange? Okay. So let's go ahead and type these into our calculator. So that's about 94.56. And that's about 73.88. And that's about 0.906. And that's about 0.422. Or sorry, 423 maybe. Now, since the unit vector is 1, I know the magnitude of the projection of P onto R is really just the dot product of P and R. Are we okay with why that's true, Ange? So to do that, I'm just going to do the product of the x's plus the product of the y's. And when I do that, that'll give me the desired result, which was about 116.92 lbs. Correct? So because R is a unit vector, its magnitude is 1. I can do that whenever I'm projecting onto a unit vector. Okay, so whenever R, what you're projecting your vector onto, is a unit vector, that shortcut will hold. Okay? You can always do it the long way through definition, and that's always going to work. But if it's a unit vector, you can take that shortcut and just do the dot product, and it'll give you what you're looking for. Okay? And the nice part about that shortcut is even the dot product will be direction dependent. So if it's like a force going up, it'll be positive. If it's a force going down, it'll be negative. So that's nice and also. If the force is like resistance, is a resisting force, it would be negative. And if it's a like assisting force, it would be positive. You kind of get what I mean by assisting and resisting? Would we like to do any others here? Colette? Okay. So 50 says a crate weighing 80 pounds is being pulled up a ramp at an angle of elevation of 29 degrees with a force of 30 pounds. The ramp has an angle of elevation of 22 degrees. What is the amount of force being directed up the ramp? So here I read three vectors. I have the gravity vector, which is going to be the weight of the crate. And the direction of gravity is always 270 degrees. So I have 80 cosine 270 and 80 sine 270. I have the vector for the pull, which is 130, and then the direction is 22. So I have 130 cosine 22 and 130 sine 22. And then I have the ramp. I'm not given any information about the ramp other than its angle. So I'm going to choose the magnitude or the length of the ramp to be 1. Oops, these are supposed to be 29s. I misread that problem. Those are 29s. This is the 22s. Everybody so far so good? Okay. So when I type these into my calculator, the first one is 0, negative 80. Then I get 113.70, comma, 63.03, and then 0.927, comma, 0.735. 0.375. Sorry, did I misspeak? My apologies. I wrote it down correctly at least. Sometimes the words on the way from my brain to my mouth get jumbled. Ever happened to you guys? Yeah. Okay. So to figure out the amount of force being directed onto this ramp, I need to take the amount of force going up the ramp. So that's going to be from the pull vector, and subtract the amount of force moving down the ramp. That's going to be from the gravity vector. In each of these cases, though, I'm projecting onto a unit vector. So I can just do the dot product and because the dot product is direction specific, I can really just, this dot product of G and R is going to be a negative number, so I really should change this into addition, because I know I just need to be like subtracting the absolute values of these. Maybe it would be better to put the absolute value around it, but I like having the negative there because it kind of gives you an idea of if you have opposing forces going on. So if I'm simplifying this down, this should change from an addition or from subtraction to addition if I'm using that shortcut, because the sign is going to come out of the dot product anyways. Is that okay? All right. So if I do that, then I'd have 113.70 times 0.927 plus 63.03 times 0.375 plus 0 plus negative 80 times 0.375. And if I type that all into my calculator, I should get the desired result, which was 99.06. Is everybody okay there? Does that make sense, Colette? Let's move forward then and start on the new stuff for today. So we have one more two-dimensional topic that we'll talk about today, and then we're going to start on to the 3D things. So today's topic, two-dimensional topic, should feel fairly familiar. The things that we're going to be doing today is going to be very much like things you did in Algebra 1. They're just going to be like the vector version of it. So before we get started, I'm going to define a third way to represent a vector. Or maybe it's a fourth way. I don't know. Let's say another way to represent a vector. This is what we're going to refer to in the book pages as IB component form. Now, when I learned this, this material as a student, we called this a column vector. You could also refer to it as a 1x2 matrix. But this is our vector and component form. If we were going to write it in this IB component form, we're just going to write it like this. So we're going to write the components vertically. And instead of using a wedge, we're going to use a parenthesis. That's all. Everybody okay with that? Okay. So remember back to your Algebra 1 class, when we talked about writing equations for a line, what was the form for an equation for a line? Good. Y equals mx plus b. It's like the one thing from Algebra 1 that everybody remembers, right? If I asked you to write the equation for a line, what kind of information could I give you and ask you to do that? Slope and y-intercept, okay. Now the y-intercept this is really just a specific version of just slope and a point, right? The y-intercept is a point. But really, if I give you the slope at any point, you can still write the equation for a line, right? Okay. What else could I have given you and asked you to write the equation for a line? 2 points. Very good. So the same is going to be true when we start writing a vector equation for a line. We're either going to need the slope and a point, or we're going to need 2 points. So the vector equation for a line is going to be the vector r is equal to the vector r naught plus the vector v times the parameter t. So t is like the independent variable in this problem. We call vector r naught the point vector. And we call vector v the slope vector. And then I guess we can write that t is just a parameter. Okay. We usually reserve the term parameter to refer to a variable that's the independent variable of multiple variables. So I'm going to pick one value of t, and that's going to give me a separate value for x and y. That's why we're going to call that a parameter rather than a variable. So that's usually just a little bit of convention. But it's basically just a variable. Yeah, that's like the 0. So like r naught is the way you read that symbol. Okay. So let's look at an example. Let's say we have the line y equals 1/2 x plus 1. And we want to write the vector line equation for this. The first thing I'm going to do is identify the slope for this line. The slope for this line is 1/2. Great. So using that, I'm going to write the slope vector. Remind me again, how do I calculate a slope? Rise over run. That's the same thing as change in y over change in x, right? So the slope vector is going to be x coordinate on top, y coordinate on bottom. So what number are we going to write on is the first component in my slope vector? 2. And what number are we going to write on the bottom? 1. That's pretty easy. Okay. What's a point on this line? So a point is an ordered pair, so just a single number is not okay. 0, 1 is fine. That's just the y-intercept. Sure. So if I want to translate that into a point vector, what would I write? 0, 1. Remember, x is the first one and y is the second one. Okay? So then I can say r is equal to 0, 1 plus 2, 1 t. Everybody good there? So the way I would generate points then for my line is by picking values of t. So let's just kind of demonstrate how that works. Pick a value for t for me. I'll go with the first one I heard, which was 3. So if I have 3 times the vector 2, 1, what kind of operation is that? That's scalar multiplication. How do I perform scalar multiplication? I multiply the scalar to each component. Everybody good there? Now what I have is vector addition. How do I add 2 vectors? I add the x's, and then I add the y's. So what this tells me is 6, 4 is a point on the line. Everybody feel okay there? That's pretty easy, right? We're just doing the vector version of these things from Algebra 1. Let's look at another example. So let's say we wanted to write this vector equation, r equals 3, negative 1, plus 2, 3t in slope-intercept form. Remember, slope-intercept form is? Okay. So what is the slope going to be in this vector line equation? So remember, this is my slope vector. So the slope is the y over the x. Everybody good there? Okay. And what's a point on my line? Negative 1, 3. Because that's the point vector. So I can say that negative 1 is equal to m times x plus b. Or when I solve for b, I get negative 11 over 2. So I can say y equals 3 over 2x minus 11 over 2. Is everybody okay with that? Sure. This should feel very familiar, though, as something you have done several times, right? Writing the equation for a line. The only thing that requires anything new is how we're translating the vector equation to get the slope and the point. Abby, what are you looking at? Okay. You're making faces like you couldn't read something or...
Is it 3y though?
So 3 times 3 halves is 9 over 2. And when I subtract 9 over 2 from both sides, I get 11 over 2? Or negative 11 over 2?
Is it negative 1x? So maybe one
Oh, sorry, I just wrote down the wrong order. Yeah. No, you're making faces, and you're usually one that pays careful attention to what's going on. So I want to make sure that that's a big one. Everybody, did we catch this? I wrote that point down wrong initially. So I did all the work correctly after it, but I wrote down the point wrong. Of course.
Bye, Kira.
Okay. So let's say we want to find the intersection between these two vector line equations. So remind me again the 3 ways that 2 lines could intersect, or the 3 results we could have for this kind of a problem. So I want to find the intersection of 2 lines. What are the 3 different results I could have? Well, let's start with the obvious. Yeah, Maria? Okay, so you could have no solution if the 2 lines are parallel. Or you could have one solution if the lines intersect, which could be there perpendicular, but they don't have to be perpendicular, but one intersection. And the third result is if they're the same line and you have infinitely many intersections. We say that those 2 lines would be coinciding if that happens. So those are the 3 possibilities. More often than not, what's going to be the result? Get one solution, right, where they intersect just one time. Okay. So the first thing that we want to do here is I want to do, stop talking please, is I'm going to simplify this part. and I'm going to rewrite these vectors in a component form. Everybody okay with what I did there? That is a 2 plus 1s. So 2 plus 1s. So using that, what I can say now is I know that x is equal to 2 plus 1s. And I also know that x is equal to negative 1 plus 3t. So I can say 2 plus 1s is equal to negative 1 plus 3t. I'm going to move this so that my s's and t's are on one side and my numbers are on the other. And then I'm going to do the same thing with the y's. So if I take this together, I have this system of two equations. And oops, sorry guys, 1s, 3s. And I'm going to try, yes, JJ, of course. And I'm going to now solve this system for s and t. What is the fastest way that we know to solve a system of equations? Substitution is a way to solve it, but I would argue there's a faster way. Elimination is a way to solve it. I'd argue there's a faster way than that. So think back to your Algebra 3-4 class from last year. We did this problem and showed you how to do this problem using only your calculator. We're going to use a matrix, okay? And then we're going to do the row reduced echelon form, or RREF, on that matrix. Okay. Okay. So I'm going to start by opening the matrix menu to my calculator. So I'll press second and then the matrix button. Inside the matrix menu, I'm going to move my cursor to the Edit tab and select one of the matrices to edit. I'm going to do mine in matrix A. My system has two equations, so I'm going to need two rows. And it has a column for the s's, column for the t's, and a column for the answers. So it's going to need three columns. For the first row, I'm going to type in the coefficients 1, -3, and then -3. For the second row, I'm going to type in the column, or the row, the coefficients here, 3, -5, and then +1. You can see that I've already done this because I did this problem twice today already. Is everybody okay with how I've set that up on my calculator so far? Okay. Now that I've typed my matrix into my calculator, I'm going to exit back to the main screen. I'm going to go back into my matrix menu. But this time I'm going to go over to the Math tab. And I'm going to scroll all the way down until I find the RREF command. I'm going to press enter. That's going to put the command on the home screen. Now I just need to retrieve that matrix A from the matrix menu that I typed my matrix into and press enter. Okay. And somehow now this matrix gives me my result, my answer. So the way I interpret this matrix is I read it one row at a time. The first row says 1s plus 0t is equal to 4.5. Or just that s is equal to 4.5. The second row says 0s plus 1t is equal to 2.5. Or rather, just that t is equal to 2.5. Is everybody okay there? Great. So, now what do? I have values for s and t. Is that my point? No. Right? These are parameters. So I'm going to take either one. It doesn't matter. For the sake of argument, let's take s. And we're going to plug that back into our original problem here. And when I do that, I'm going to get 17.5, 4.5. So that tells me my point is, yes, sir. Of course. So there's my point. Okie doke. If I had picked T and plugged that one, I should get the same result. Yes, sir. All right. That's the last two-dimensional vector topic that we're going to talk about in this class. What I'm going to start talking about now today is three-dimensional vectors. So the three-dimensional coordinate system has three axes. It has an x, y, and a z axis. The way that you want to visualize this is the solid lines are in the same plane as your paper, and the dashed line is like sticking out right in front of you and then directly behind into the, into the paper and out of the paper. Is that okay? So you need to use a little bit of imagination to kind of picture this in your brain, because you have a three-dimensional object that we're trying to draw in a two-dimensional space. So you have to use a little bit of perspective when doing this. Okay? So those of you that have art class and have done some perspective drawing, this should feel a little bit more natural to you. So the way that the convention we have for naming these axes is the axis that comes out of the sheet of paper is the x-axis. This is the y-axis, and this is the z-axis. I know, you're like, why can't we name x, y, and z the way I would expect? I don't know why, but this is the convention in which they're drawn. Okay. Just so we're aware, this is the positive side of the x-axis. This is the positive side of the y-axis. And this is the positive end of the z-axis. Is everybody okay there? So if I'm describing a point in 3 dimensions, how many components am I going to need to describe that point? 3. So I'm going to need to describe my point as an ordered triple. It's going to have an x component, a y component, and a z component. We're always going to list those components in that order. It's alphabetical order. So let's say that we wanted to graph the point 2, -3, 4. So I'm going to start by drawing in some tick marks on my axis. So I'm going to draw 2 tick marks on my x-axis on the positive end. I'm going to draw 3 tick marks on my y-axis on the negative end. And I'm going to draw 4 tick marks on my z-axis on the positive side. Is everybody okay there? Okay. I'm sorry, what?
Why is this equal to x usually?
That's just the convention that we're going to use to draw it. Okay. I don't have a good reason for it. That's just what we've decided to do.
Oh yeah, you know what I'm saying. Shut up, dude. You know what I'm not.
Okay.
Just leave me alone.
Okay. So I'm going to start by finding the point 2, 0, 0, which is right here on the x-axis, right? I'm going to draw a line now, starting here, parallel to the y-axis. Everybody okay there? Now I'm going to find the point 0, -3, 0 on the y-axis. And I'm going to draw a line that's parallel to the x-axis. Everybody okay there? What this really makes is now like a little parallelogram down here. Can we all see that? Okay. So I'm going to now draw from the origin up to the z-axis. Everybody kind of see that? And I'm going to draw a segment that's parallel to the x-axis. Okay, and I'm going to connect it here. Everybody see that? And then I'm going to draw from this spot, I'm going to draw a parallel to the y-axis. And I'm drawing up to here. And this spot is my point that I'm interested in. Okay. So if you wanted to draw the rest of your prism there, it would look like this. Okay. So it's important that you realize, or that you remember, that what we're drawing is in 3-dimensional space. So we have to use a little bit of perspective. Those of you that have had art class, quick show of hands, that have done 3D like perspective drawing in art. This is the same kind of idea that we're doing here. Okay? So to plot these points is not easy to just like draw it on a sheet of paper like we can in 2 dimensions. Right? We have to imagine, we have to draw our like 3D space and then make sure that the point is in the correct corner of that 3D space. Right? So like this point down here is 2, -3, 0. So we have to go 4 units up to get to this point, 2, -3, 4. So this is like 2 this way, 3 that way, and 4 that way. Kind of see that now is what we tried to do. Okay. So if this still feels unfamiliar and you're not quite sure what's going on, I'd encourage you to look at the text pages. I have some good computer-generated images of this graphing process there that are better than what I can do by hand. I acknowledge my abilities here that I'm able to do by hand with a stylus on the computer. It's not easy, but I think we did an okay job there. Yeah, thank you. But that's what I want you to be able to do in terms of graphing a point. You should be able to do that. You should be able to draw that cylinder, or I'm sorry, that prism. It's a prism, not a cylinder. Okay? So in 2-dimensional space, we have a distance formula, right? Everybody recognize that? In 3-dimensional space, we have a distance formula. What do you suppose it's going to look like? Yeah, it's the same thing with one extra component for the z's. Oh my goodness, guys.
What happened?
Those are supposed to be subtraction symbols.
Oh my God. You're a cat.
Sorry. Subtraction symbols. That's a big oopsie, guys. It's the end of the day, you know. I am sweating it. Sweating it to the oldies here. That was a workout video from the 80s. A man named Richard Simmons made these workout videos. It is no relation. But they were on like infomercials like all the time. But it was like the exercise was like dancing to these oldies music.
Were you facing that?
No, but I saw it on TV like at least twice a week.
You won't judge it.
I didn't, but. All right. We also have a midpoint formula for 2 dimensions. So the midpoint is just the average of the coordinates. What do you suppose that looks like in 3 dimensions? It's the same thing with a extra component. Yeah.
Jesus.
So let's say we have these 2 points, and we want to find the distance and midpoint between them. Everybody okay there? Just filling into a formula, right? If I want to do the midpoint, I'd get that. Everybody okay there? So for Monday, nope, we don't meet till Tuesday, right?
Yeah.
Oops, that's not right. Okay.